we are discussing the topic of concurrency control, and we have seen that concurrency arises in multi-programming or multi-processing when more than one simultaneous programs may be or transactions may be in an active state. And the issue of consistency arises here because these programs may access shared data and update shared data. And if they update it in any arbitrary interleaved fashion, some of the consistency criteria of the database or of the transactions as such may be violated. So we must ensure that the transactions can execute in an interleaved fashion, but the consistency criteria is maintained. For this, any arbitrary interleaving of more than one transaction which are active is called a schedule. Among the concurrent schedules, if the two transactions are parallelizable or they can run together concurrently, we have got what is called a serializable schedule or a serial schedule. For example, if there are two transactions T1 and T2 which can run concurrently, then they are run serially if one is run after another is completed. One starts after another is completed. And obviously, the order in which they run serially does not hamper the consistency. That is a core criteria. That is the basic criteria which defines that they can be executed one after another, is that their sequential ordering does not affect the consistency criteria at all. There are some schedules which are actually interleaved, that is, they are working in an interleaved fashion, and they are called concurrent schedules. A concurrent schedule may be serializable if its result is equivalent to any one serial schedule. On the other hand, a concurrent schedule, so all serial schedules are valid schedules, but all concurrent schedules are not valid, may not be valid schedules because they may violate the consistency criteria. Some concurrent schedules may be equivalent in their output to serial schedules, to some serial schedule. Such concurrent schedules are called serializable. Other concurrent schedules which are valid may not be equivalent to a serial schedule, but still may be consistent. So those concurrent schedules are also valid schedules. We shall now study how to detect whether a schedule is inconsistent and how the whole process of concurrency control is to execute transactions in a interleaved or concurrent fashion and try to minimize the amount of invalid schedules being executed and inconsistencies happening, so that the transactions are not rolled back and execution does not have to restart again and again. Let us go back to some of our examples and let us see some of our old transactions. Now, if we are to analyze whether a transaction is actually consistent or is going to behave consistently, it is quite difficult to do it by analyzing what the program is trying to do, because trying to analyze the meaning of a program while execution is a much more tougher job, and some of these issues are actually unsolvable in the sense that they cannot be solved on the computer at all, what a program is trying to do, and it will take more time to analyze that. So in order to put an abstraction to what we are trying to do, an easier way out, though it will not take care of all the cases, is to consider only the read and write operations and just forget about the rest of the intermediate aspects. And let us see, by analyzing the read and write operations, whether we can detect potential pitfalls. What will happen is, if we remove these while analyzing our results, we will be able to detect, if we detect an inconsistency, it may be consistent, may not be consistent. That is what can happen. Every inconsistency will be detected, but every detection may not be inconsistent. So, we will take that into account because we have to do it quickly. So, we shall not bother about such schedules anymore. We shall abstract a schedule, and the schedule will now look like this. We are just bothered about what are the read-write operations taking place on the disk, because in the memory there can be no inconsistency. We are not dealing with shared memory at this point of time. We are only dealing with shared disk problems. And this will be read X, write X, read Y, write Y. And now we can have various schedules. If we analyze this, we will see we can have a schedule which is read X, write X, read X, write X, read Y, write Y, this is the equivalent of this schedule. Now 1, 2, 3, 4, this is the equivalent of this schedule. We are not bothered about what is being done in the middle. Later on we shall see, by removing that information, what we have lost. But let us see what are the advantages we gain by removing that, because we don't have to analyze what actually is happening to the data. We will assume that in the worst case the data is modified arbitrarily. We just don't know what is going to happen. It is just modified. Read followed by write is data is modified. Read followed by write means data is modified. Now this is a schedule which is equivalent to the schedule T1 followed by T2. We know by looking at this we can say that this is equivalent to the schedule T1 followed by T2. That is our way of looking at it. But how will we formalize that this schedule is equivalent to a serial schedule? So there are various ways in which we can try and detect that a schedule is equivalent to a serial schedule. If a concurrent schedule is equivalent to a serial schedule, obviously it has to be consistent and it has to be a correct valid schedule. So our first approach in this mechanism will be to, when a schedule is defined, we shall try to see whether this schedule is potentially valid or invalid. And how will we test whether it is potentially valid or invalid? Our only test criteria will be, if it is equivalent to a serial schedule in some form, then it is said to be correct. We will allow it. If it is not equivalent to any serial schedule, then we will not allow it, fearing that there may be inconsistency. For example, since this one is equivalent to a serial schedule, we will allow it. If a schedule is read X and then read X, write X, then this write X, then it may not be equivalent to a serial schedule. We will not allow it. So how will we detect that? So our first criteria of validity is whether, if it is equivalent to a serial schedule, we allow it. So how will we detect whether a concurrent schedule is serializable or not? So there are various ways to detect whether a concurrent schedule is serializable or not. and we want to do it quickly also. We do not want to spend half an hour of time to detect whether this is serializable or not. You can just run them one after another in 5 minutes. So we must also take that into account. The first mechanism for doing that is called the conflict serializability condition. One algorithm for detecting whether two schedules are concurrent are serializable is a method called conflict serializability. Now let us try and see what conflict serializability means. Conflict serializability tries to, given a now we are doing it only with two such transactions. It can be 3 or 4 transactions may be there executing simultaneously. This all these techniques which we will discuss holds for more than one transaction. Now the core idea behind conflict serializability is to try and swap, is to try and move. Behind any serializability algorithm is, given a concurrent schedule, just try and move the instructions up or down and see whether you are violating any consistency criteria. Let us see. Here this one follows this, then this, then this, then this, then this, then this. Now suppose I shifted this up here. That is, if read y was done between read x and write x, there would be no problem. It is still correct, because y does not even have any effect on x. So we can move this read y along this right up to here. Obviously we should not move read y before this, because this is a transaction. We cannot just reorder the operations in a transaction. That we are not allowed to do. In a particular transaction we must maintain the order in which they are executed in that transaction. But we can move this right up here without changing the result. Simple question is, this statement can be moved right up here without changing the result. This can be moved right up here without changing the result. How will we move it? We will check. If we want to swap these two, we will check whether they are in conflict. Two instructions are not in conflict if they access different variables. So we can swap them. So we swap. Then we see this and this. They are not in conflict because they access different variables. Swap. Similarly, this goes up and swap, it goes up. So we define a swap operator. And we see, using that swap operator, if we can transform a concurrent schedule to a serial schedule. Let us see whether we can do this. Can we move this read above this write? They access the same shared variable. And if we move this read above this write, it is going to change the data. It is potentially going to change the result. So these two instructions are in conflict and swapping is not allowed. So we cannot move this up like this, nor can we move this up above this, but we can move this right up. So once we are allowed to do that, we will see that we will reach a concurrent schedule, a serial schedule from a concurrent schedule. So the idea behind conflict serializability is to detect whether you can transform a concurrent schedule to a serial schedule by a set of non-conflicting swap operations. So now let us go a little more into the definitions. Let II and ij be two instructions such that II belongs to a transactions T, say P, and ij belongs to transactions Tk. and if they access the same data item II and Ij access data item X. If they do not access the same data item, swap is allowed. Now, if they access the same data item, what are the four possibilities? II is read X and Ij is write X. II is read X, Ij is read X, II is write X, and Ij is write X, and II is write X, and Ij is read X. Now, if II is before Ij, can we swap them? Here. Sorry. If it is II is before Ij in any schedule, can we swap them? This is conflicting. Sorry. We cannot swap II and Ij. If both are read, can we swap them? We can swap them. It does not matter. If both are read, we can swap. So, this is okay, this is not okay, this is not okay, sorry, and this is not okay. So, we can swap them either if they do not access the same data item, excuse me, or only this occurs. Otherwise, we cannot swap them. That is the. What about both writing the same data? If we do not know what is being written, we just cannot swap them arbitrarily. Because look at it here. If we have read, let us see an example when both write the same data. Can we swap them? As it is, the transaction is inconsistent, but we are just seeing whether swapping is allowed or not. Given an arbitrary concurrent schedule, they are swappable only if by swapping the actual result does not change. That is our criteria. It is true that we will see example in which swapping is not allowed and the transaction is consistent. That can be there, as we have seen before. That is because of one or two very important criteria. One is we have removed all the intermediate operations. The intermediate operations itself may be such that even if you swap on a conflicting, even if you make a conflicting swap, it does not matter. The transaction is allowed. The transaction will give the correct result. But if we are given an schedule like this, can we just shift them one after another? We just don't know. For example, can we shift this up? This can be shifted right up to here. But can this be shifted up before this? This cannot be shifted up. This cannot, this is not equivalent to this is not equivalent to this. So this one is equivalent to this one. Alright, these two are equivalent, but this one I cannot shift this right up before this. That is, this one, these two are equivalent. Alright, it does not matter because I can move this read P right up to here. But 1 minute. But if I say read X, sorry, write X, and read P, this is not equivalent to this, nor is this equivalent to this. But this one is equivalent to, this is not equivalent, but this one is equivalent to these two are equivalent. I am sorry, these two are also not equivalent. I am sorry, these two are also not equivalent. So you see that you just cannot move the write up arbitrarily. This is one serial schedule, this is the other serial schedule. This is another intermediate schedule which is equivalent to this schedule. Alright. This is another schedule. Now, what is the relationship between this schedule and are these two equivalent schedules? These two are not equivalent schedules. You just cannot say that they are.
In fact, the example which you have taken is not consistent. Read X and write X, and then followed by read P and write the top corners. Yes.
This is one transaction T1 and this is another transaction T2.
So this means that there is one read X in T2 which is before this.
No, it reads a value from a variable P and writes it into X. It reads my salary and writes out my PF. There is no problem.
Does it mean that the current schedule we have in our hand, that will lead to no inconsistency? Before deriving before checking, this means
what we are trying to do is trying to analyze a concrete schedule. Before actually executing it, we are trying to quickly analyze and see whether this schedule may lead to inconsistency or not. We want to do it quickly, so we want to remove certain information and we want to be sure that our detection is correct, in the sense that if there is inconsistency, we will detect it. But that does not mean that if we detect it, there is bound to be inconsistency. We will come to that later on.
consistent schedule. That first of all we have to ensure that this schedule is consistent.
We have to ensure,
then only we can check.
Then only we can execute. Whenever the scheduler is doing it, before it, the scheduler does a planning phase in which it plans out. I will do this in the next phase. When it does this planning is checked whether this plan is correct or not. So let us come back to our case, what we were doing in conflict serializability. The terminology says that we will have a swap operation and our swap operation allows instructions of transactions to be swapped. So, given a schedule S, we are allowed to swap instructions if they access different data items or if both are read on the same data item. Now, if we have two schedules S1 and S2, we say that they are called conflict equivalent if S1 can be transformed to S2 by a series of swaps. Such swaps based on this criteria. If S1 can be transformed to S2, then S2 can also be transformed to S1. There is no problem, because swap is a equivalent criteria. We will see. Just see this criteria. If S1 can be transformed to S2, then obviously S2 can also be transformed to S1 by the same methodology. So, by the conflict serializability that we have defined, we say that two schedules S1 and S2 are conflict equivalent if one can be transformed to another, and we say that a schedule S is conflict serializable if it is equivalent to any, if it is equivalent means here conflict equivalent by the method of conflicts that we have defined, to any serial schedule. So, a formalism has now been defined in which we define the concept of a conflict and a swap operator, and using this conflict swap operator, we try to find out whether two schedules are equivalent, and using this concept of equivalence, or which we call conflict equivalence, we try to find out whether a schedule S is equivalent to any one serial schedule, and if it is equivalent to any one serial schedule, then we will say that this schedule is consistent. This schedule can be allowed to go through. That is the whole process by which we argue. Now, how will we do it quickly? How will we do it quickly? Let T1 and T2 be two transactions. All right. And let us see an example here. Let us see this example. We have got two transactions, T1 and T2. Now, if we cannot swap this beyond this, we say that there is a link from T1 to T2. That is, this cannot be moved over this. This one cannot be moved above this one. So, this part of T1 must execute before this part of T2. So, if it is to be serializable, then T1 must execute before T2. This arrow means that if these two are to be serialized, then T1 must execute before T2. Why? Because this read cannot be moved over this right. This arrow will come either because of this criteria or because this read cannot be moved above this right. All right. So, we now have this arrow, and there is no other arrow here because this one can be moved right up, this one can be moved right up. So, given two transactions, here there is only one arrow. Suppose we had here a transaction which was like this. This is a schedule where this is T1 and this is T2. This is T1 and this is T2. This one cannot be swapped before this. So there is an arrow like this. This one can be swapped right above this. This one can be swapped above this. But this one cannot be swapped beyond this one. Please note that this part cannot be done before this part if T1 is to exist. So we will have this arrow as well. And whenever we have a cycle in this conflict graph, we can always say that this schedule is not serializable, is not conflict serializable. Let us have more than one, let us have 3 or 4. You just set up this conflict graph. And once we set up this conflict graph, we can say that this schedule is conflict serializable. What is conflict serializable? It is equivalent to any serial schedule. If it is to be conflict serializable, then this conflict graph must not have any cycle. So setting up the conflict graph is quite easy. You just try to shift them up and see whether a conflict is occurring. And this can be done very quickly, and checking whether a graph is acyclic is also very easy. So reasonably quickly, because we have removed most of the operations, we have just left the read and write operations. And we have removed all the other operations. By removing all the other operations, we are able to say that this result is a correct result. So conflict serializability criteria can be tested easily, but let us see whether conflict serializability really is a good criteria, in the sense that whenever instructions are consistent, can be detected. Let us take this example. Let us come back to this example. Please note, we have got read x, write x, read y, write y, read y, write y, read x, write x. Here, read x, x is assigned x minus 100, write x. Read y, y is assigned y minus 60, write y. Read y, write y, read x, write x. An abstraction of this is this. So this one we have said this is not serializable, and according to our criteria, we will say that this is not consistent. But we have seen just like some time before that even if we run them like this does x minus 100 and y plus 100, this does x minus 60, y minus 60 and x plus 60. Effectively, when they run together, one deducts 40 and the other adds 40. In any sequence you run them. This one, this. But if you put this right later on, then you may be, even if you move this right down here, there is no problem. You can interleave this one in any fashion also. You will still get a correct result, because effectively both of them together. So our consistency criteria is not capable of checking. That is, as I have said before, our criteria is sufficient. If we say that it is conflicting, then it may or may not be inconsistent. But if it is inconsistent, we will definitely find it to be conflicting. That is the criteria. Now let us come to the argument which we were doing with that read P and write Q. The question is this is not conflict serializable according to our criteria. This does not have intermediate operations. This is an abstracted information. But is this schedule correct? Is this schedule consistent in the sense that is it equivalent to any serial schedule? Not conflict equivalent, we know, but logically is it equivalent to any serial schedule? If we move read Q down, will it give the same result? Does it?
No. The right Q is there.
But if we have such a schedule, what will we say? Will we say that this is okay? Will we say that this is equivalent to a serial schedule? Let us say this one. Is equivalent to this? This is one. This is the other. These are the two serial schedules. This is one serial schedule, this is the other serial schedule. Now look at this one. It reads a particular value of x, does some operations and writes that value back. This one simply does something from somewhere and writes on to x. So why? The argument is that this is quite consistent. There is no problem with this schedule. This schedule is consistent. Why? Because it reads a value of q, does some operations and writes it back. This one writes into q without reading it. So it just writes something into q. It does not modify q in the sense that it does not read q, modify it and write it. It reads from somewhere else and writes q. So maybe somebody is writing some information into this data. Now if these two are concurrently executable, then if this was written and this was done, it would have been okay. So if this occurs and this is written in between, this is equivalent to this operation being not there. So this will not really change the inconsistency of your data. It is not going to affect the consistency of your data at all. And this is something which is not detected by our criteria of conflict serializability, as you were saying a little while ago, that write may be consistent sometime. So our conflict serializability criteria cannot check semantic conditions like this, and it cannot check certain conditions like this. In order to put such things as, in order to make such a schedule also as a consistent schedule, we just add some more criteria to our conflict serializability, and we have what is called view serializability. View serializability has the following criteria. Two schedules S and S dash are said to be view equivalent. When are they view equivalent? If. Now we don't have any swap operator now. We have just three criteria which are to be checked. If for each Q, if Ti reads the initial value of Q in a schedule S, then Ti must in the new schedule S dash also read the initial value of Q. That is quite fair. Whoever reads the first value of Q must also read the first value of Q here, for every Q. Secondly, for each Q, if Ti executes read Q in the original schedule S, and this value was produced in Tj, that is, there was a write Q in Tj which produced Q, and then Ti read it after that. Then in the new schedule also, in the new schedule S dash, the Ti must read the value of Q that was produced in Tj. The language just means this. If in one schedule this reads Y which was produced here, in the modified schedule this will read Y which was produced here. This may be moved right down up to here, but this Y is produced by T2, so it must read that Y produced by T2. And finally, for each Q, the transaction that performs the final write Q operation in S must also perform the final write Q operation in S dash. So the person who reads it first must read it first in the new schedule. The person who writes it last must write it last in the new schedule. And if I read it, if T1 reads it and T3 wrote it in a schedule S, then in the schedule S dash, T1 must read whatever T3 wrote. If we maintain this consistency, then we will still have serializability condition, in the sense that if there is inconsistency, we will detect it. So such a condition is called view serializability. And view serializability encompasses, you can easily prove that whatever is conflict serializable is view serializable. There is no difficulty in proving that. But whatever is view serializable need not be conflict serializable. For example, this one is view serializable. He reads the initial value and he wrote the initial value. He wrote the final value. Okay. Now, however, testing of view serializability is difficult, in the sense that while conflict serializability can be done by testing acyclicity, view serializability cannot be done by testing by acyclic testing. View serializability is much more complex, and in fact it has been found that view serializability is NP complete. Testing whether it is view serializable is NP complete. Now once it becomes NP complete, we will see that it is it will take so much time to really check whether it is view serializable that it may not be useful at all. So this is one set of criteria by which you can check whether the schedule is okay or not, and then we will allow it to go for scheduling. The other condition, the other methods of doing so, there are several other methods of doing so. The second method is more related to the OS type of a scheme, where we use in operating system in order to, this is called the mutual exclusion problem in operating systems. It is the same mutual exclusion problem in concurrency control, and there you use what is called the concept of semaphores, or the concept of mutual exclusion, whatever means you have for doing mutual exclusion, the PV semaphores, the wait signal mechanisms, or the loop mechanisms of mutual exclusion. Here in database management systems, we will try to adapt that philosophy and develop what are called locking protocols. Locking and unlocking, which is the same as the P and V operations. Lock and unlock are related to the P and V operations of semaphores, which is used in memory based sharing. Here we have got disk based sharing, and there it is memory based sharing. So we will just adapt it back here in database terms. It will have slight differences, but the philosophy will be the same. And we will see there the difference is that you have to write the program correctly. Now a schedule will not be checked. It will wait on that lock or semaphore, and it will be released from that semaphore. That is how the process will go on. So we will study that in the next few.